All right, so as I mentioned earlier, there's a fair amount of models that have distributional assumptions. And these distributional assumptions can be centered around the shape of our data. And so when a certain feature may be skewed in one direction or the other, this can actually hinder the model performance. Now, which models require this and which do not? Right now, as you're starting to learn about the different algorithms, I wouldn't be too worried about keeping all this information in mind. Just realize that certain models can have certain requirements that we need to fill around the distribution. Now, some examples are going to include such as linear regression, any of like the linear regression type of family models, linear regression, logistic regression, or regularized regression. Right? They can all be negatively impacted by skewness within our data. Neural networks is another one. And like I mentioned before, there's some models that really don't care about the distribution of the values. Decision trees in random forests and gradient boosted machines, those are all tree-based algorithms, and they really don't care about that distribution. But don't get too hung up in that right now. Just realize that this is an issue that can pop up and you should be aware of. But we can go ahead and correct this problem with the distribution. And any of those models that are not hindered by the distribution, like if there is a normal distribution of a feature, just realize that if we go ahead and we modify the distribution to make it more normally distributed, most algorithms are not going to be negatively impacted by that. So when all else fails, go ahead and correct for any potential skewness in our features. All right, so what does this actually look like? So if we were to look at the ground live area, this is the total square footage of homes, you can see that we have the skewed distribution, right? So we have a lot of homes down here around 1,000 to 2,000, but then we have some that have much larger square footage. But we are kind of capped down here on the left side, like just how small a home can be. So this naturally leads to a right skewed distribution where we have this long tail. Now it's this tail that can cause problems with certain models, and what we'd like to have is a much more bell-shaped or normal-shaped distribution. And so we would like to change the ground living area feature to look more like this on the right. This looks much more evenly distributed or normally distributed or bell-shaped curve looking. Okay, this is what we'd like our features to get to. We call this normalizing. And so it's normalizing features that change the distribution to be not skewed one way or the other. Okay. Now this changing the distribution, although we are kind of changing the values of that square or that particular feature, we're actually not really changing the differences that exists between observations. Okay, we're just simply applying some kind of mathematical formula to make a change in what that value is to correct for the distribution. Now, how do we do that? Well, there's a few different ways. We can use a log transformation. A log transformation is almost going to always take a right skewed distribution and make it more normally curved. In fact, that is what's being applied here behind the scenes. We took this variable here, we applied a log transformation to all the values, and that resulted in the distribution looking like this. Now, not all distributions are right skewed. Sometimes they are left skewed. And also sometimes the way that they are skewed is not always consistent. So although a log transformation may help, it's not always going to help. And there's actually a transformation that's similar to a log transformation. We call this a Box-Cox transformation, but it's actually more flexible, and it's going to help transform a particular variable, regardless of if it is a right skewed or left skewed, to be more normally distributed. Okay, so Box-Cox transformation is more flexible than a log transformation, and that's a good thing. Now, there is a problem with the Box-Cox transformation, And that's that if you have negative values or values less than 0, a Box-Cox transformation actually cannot always be applied. So there's a special case that's called a Yao-Johnson transformation. And this is a very similar transformation to Box-Cox, but it also works with negative values as well. Right? So the way to think about this is Yao-Johnson is a special case that will capture Box-Cox and log transformations. A Box-Cox transformation is a special type of algorithm that also includes log transformation. So you can kind of think about this as like a hierarchy. And honestly, the most flexible the most flexible one that can be applied in almost any scenario, whether it's right skewed, left skewed, positive values, negative values, is Yao-Johnson. So I always just recommend go ahead, use Yao-Johnson if you are trying to change a skewed distributed variable into a normally distributed. And so we have these different step functions, just like we saw in the previous video, that we can apply these and just add them to our recipe.